Okay, here we'll try to explain a couple of things, right? Like how to interpret a VT graph into the body's actual motion, right? And also we'll discuss mainly how whether negative acceleration implies deceleration or not. Okay, we'll try to address this question, which is a common question for students. Right, so here I have a VT graph of a body split nicely into five parts, right? A, B, C, and D, and E, all right? And I want to try and visualize what happens to this body using the VT graph, right? So we know that area under graph actually gives me change in displacement, right? So this is change in displacement, this is delta S, right? And in this case, delta S is a positive value because it's half times 5 times 50, right? Which everything here is positive. So delta S will be positive, right? So if I want to look at how this body moves, I draw a diagram to show how this body moves. This is my start point, it's my reference position, right? Then let's call this area A, all right, for simplicity's sake. Right, so let's say this area A is half, area A is actually can be calculated by half times 5 times 50 lah. But let's just summarize this value as A, okay? So it travels some amount of area A towards the right, right? Because this is positive area, that means positive change in displacement, which means I move towards the positive convention, right? So if I look at area B, it's still positive area, right? But clearly it's bigger than area A, right? So area B is larger than area A. I move some more towards the right. Right, area C is slightly smaller than B, right? Actually, it's half, right? So area C is smaller than B but larger than A, right? So area B is, area C is still positive area. So I'm still moving right, okay? But what is unique is when I come to this area here. This is the first time my area become negative, right? Which implies that my delta S becomes negative as well because delta S is the area, right? So my change in displacement for the first time is negative, which means that I'm moving towards the left, right? Because right is taken to be positive. So at this position here, I actually reverse direction in this area D. So area D is pretty small. Okay, I can go and calculate this area. But if I calculate this area, it will be half times minus 2.5 because it's minus 2.5. Half times minus 2.5 times 50. Alright, and this will give me a negative value because of this negative 2.5. When I have negative area, it implies displacement is negative. It means I'm moving towards the left, right? Also note that this point is very critical, right? Actually, velocity is 0 here, right? Velocity is 0 normally implies a turning point, right? Normally, not always, right? There are times whereby the graph could carry on going up again, then it won't be a turning point. It will just be a rest point. But in this case, my velocity becomes 0. It means I stop for a while. And at this point where I stop, I actually turn around because I look at this area is negative. Right? That means it's opposite. I'm traveling opposite direction to where I initially traveled, which is positive here. Right? Then I check this area again. It's still negative. That means I'm still moving left. Right? So this is E. So this is how the actual body looks like from A, B, C, D, and E. Right? So I move right more. I move right. I stop for a while here. Right? I move left. And because these two areas are negative. Right? So now we have an understanding of how this body actually moves. Let's try and figure out whether we know in each part whether they speed up or slow down. Right? So in A, they clearly speed up, right? Because velocity goes from 0 to 5. That means my speed increases from 0 to 5 meters per second, right? At B, my speed is clearly constant. No need to discuss that. At C, my speed decreases, right? Because velocity goes from plus 5 to 0. That means my speed goes from a value of 5 and I approach 0. Right? So this is the point where I'm at rest, right? Remember, right? Then after that, my velocity goes from 0 to minus 2.5, right? So this is where it gets somewhat interesting because here I actually speed up. My velocity goes from 0 to minus 2.5. But if I want to figure out whether this body speeds up or slows down, I just look at the magnitude of velocity, which is speed, right? So I just realized that its speed goes from 0 to 2.5, right, in this region T, which means that my body is speeding up, right? Right, because the speed is going from 0 to 5, right? And likewise, if I apply the same reasoning here, I go from velocity is minus 2.5 to 0. If I want to figure out whether speeding up or slowing down, I just look at speed again. Actually, speed goes from 2.5 to 0, which means that I'm slowing down, right? So why? Because the speed is dropping lah. Okay, can. So I've already cleared the first two rows, right? This part, how to get these parts. They're quite straightforward. right? What I really want to discuss is actually how do I know whether something is speeding up or slowing down based on the direction of velocity and acceleration, right? So hopefully you notice a trend, right? That what acceleration does is it changes velocity, right? So if my velocity is towards the right and my acceleration is towards the right, then my acceleration is actually supporting velocity. It's trying to make velocity bigger, right? So that clearly implies that my object is speeding up, right? So as in this case A here, right? My velocity is positive, right? You can look from the y-axis. My acceleration is positive as well because I look at the gradient, it's a positive gradient. That means my acceleration is actually supporting the velocity. It's making the velocity's magnitude bigger, right? For B, I don't have to discuss because acceleration is 0, so velocity doesn't change. For C, the velocity is positive, but the acceleration is negative, right? So if velocity is positive, right, because you can read off the y-axis, acceleration is negative, it means the acceleration is opposing velocity, right? So acceleration is towards the left, the velocity is towards the right, correct? So my acceleration is actually trying to reduce the magnitude of velocity, right? So that's why my body is slowing down, right? Then we look at this case for in region D. Realize that the acceleration here and here are actually the same, right? Because the gradient is the same, right? The gradient from here to here is consistent. However, the way the body is moving is quite different, right? Because at this point I reach zero velocity and now acceleration is still towards the left, all right? My speed actually increases, right? So if you look at throughout this region, actually velocity is just negative. If I discount the 0 point, right, velocity is always negative here, all right? And my acceleration is also negative because the gradient is negative, right? This means that in this region, my acceleration is again supporting velocity, right? This is supporting this, which means that I'm making the magnitude of velocity bigger, which means speed gets bigger, right? And then finally, we look at this. Velocity is negative here, right? Because these values are all negative, and acceleration is a positive value, right? So if acceleration is a positive value because gradient is positive, right, then they are opposing each other again, right? So now my velocity is trying to move towards the left, but my acceleration is trying to head towards the right, right? So my acceleration is actually trying to uh, reduce the magnitude of my velocity, right? So the conclusion is very simple. Whenever acceleration is same direction as velocity, this means that acceleration is making the magnitude of velocity bigger. Or in other words, my speed is increasing because speed is the magnitude of velocity, right? So whenever my acceleration and velocity are in the same direction, I'm speeding up, right? Conversely, if my acceleration is opposite in direction to my velocity, I'm trying to reduce my velocity's magnitude, right? So whenever acceleration is opposite in direction to velocity, like in this case C and E, right? Direction is opposite direction to velocity, then my body must be slowing down, right? So that's how we look at acceleration and velocity to determine whether I speed up or slow down. Whenever they are in the same direction, speed increase. Whenever they are in opposite direction, speed drops, right? So we with that we come to the final answer. We have come to the final question of this piece of paper. Does negative acceleration imply deceleration? Right? Hopefully you can see that that is not always the case, right? So if we look at the graph here, where is negative acceleration? Right, this whole thing, C and D is negative acceleration because this whole thing is negative gradient, right? So negative gradient means negative acceleration. This acceleration is gradient, right? So negative acceleration happens here. Am I speeding up or slowing down? I'm slowing down. Negative acceleration happens here. Am I speeding up or slowing down? I'm speeding up, right? So negative acceleration actually doesn't tell you anything. Sometimes negative acceleration, right, means, like in this case, means slowing down, right? Sometimes negative acceleration, like in this case, actually means speeding up, right? So these two, at least to answer the question, negative acceleration does not imply deceleration. Sometimes it does, okay, but it does not always imply deceleration.